Okay, unmuted myself. Everyone, please give a warm welcome to Ximena Curiel, who is joining us this evening from the Yucatan. Ximena grew up in the jungles of Southeast Mexico, and in her own words, from firsthand, she observed how ecosystems degraded and how her love for all living things led her to an infinite romance between biology and design at an ecosystem level. Today, Ximena is a biopreneur who manufactures bio-based inks for fabric printing and teaches biomimicry, ethnography, biophilia, and circular economy to fashion design students. She is a product designer with a master's in science of biomimicry at ASU. Ximena became a climate reality leader, and her passion for sustainability in the design world inspired her to complete a cradle-to-cradle training program and also a certification in circular economy with the Ellen MacArthur Foundation. Ximena has exhibited her designs in the 10th London Design Week and has also earned a Star Pack Design Award for biodegradable packaging design. Ximena's color research path started 4 years ago while studying for her master's degree in biomimicry. She notes, "It is no secret that dyes and pigments used in the fashion industry are not only pollutants, but also carcinogenic, but is nevertheless happy to share that she has achieved formulations of 100% plant and fungi-based inks for fabric printing." So again, everyone, please a warm welcome to Ximena, and we're so excited to have you this evening.
Thank you, Emma.
Pass it.
Well, thank you, Emma. Thank you, Angel. Good evening. Welcome to you all. It is a great pleasure to be here. And I want to thank Central Texas Mycological Society for having me. And I would also like to thank Daniel Reyes, because he kindly made room in his lab at Myco Alliance in Yucatan for us tonight. So yes, this evening, we are going to learn about natural color, from structures in corals and butterflies, all the way to fungi color. So before we answer, or we try to answer one of the main questions in life, that is, what is color, and is color even real? We have to set the itinerary for tonight's trip. So first, we are going to learn a little bit about biomimicry. Then we are going to learn how case studies of biomimicry are emulating color from corals and butterflies, so we can understand a little bit more about color models and the color theories. After that, we will learn about light, because ultimately color is light. So we can know about the photobiology and the quantum chemistry of fungi, which is just amazing. And at last, but not least, we will learn about the amazing mycodiers out there creating a fungi rainbow of color. First stop in this trip is biomimicry. So the word itself, perhaps many of you already know, means, well, it comes from bios, which means life, and mimicry, which means to imitate. So biomimicry means to imitate, to emulate life. What makes it different from many other biodisciplines is that it has 3 essential elements. In order to explain the first one, which is reconnect, I would like you to do a quick exercise with me. Please close your eyes. Take a deep breath and imagine yourself in a natural setting, any setting of your choice. Feel the breeze dancing with your hair. Feel the sun kissing your skin. Embrace that moment in the natural setting. Take another deep breath. And open your eyes. Did any of you see humans in the natural setting? Perhaps not. And that's how deeply disconnected we are from nature. We have forgotten that we are created from rainwater, electricity, and carbon, that we are too biodegradable, that we are compostable. And in order to do biomimicry, or even to just be human, we need to let go of that perceived separation of nature. And we have to embrace the truth that we are nature. Here we can see on the left side a human lung, and on the right side the Ericium coralloides mushroom. Nature creates ramifications following the same mathematical algorithms in our lungs and in the fungi world. The second essential element of biomimicry is to emulate. We will no longer see forests as a Home Depot or a warehouse from where we can extract natural resources, but we will see nature as a laboratory of research and development, as libraries where amazing knowledge from 3.8 billion years is being achieved. How are we going to emulate nature? Well, by replicating its forms, its processes, and ultimately its ecosystems. We have on the photograph a beautiful mushroom species unidentified growing on feces, because there's no waste in nature. There's not such things as garbage or rubbish. Everything is a nutrient. And this photograph I took a few years ago is from a little tide pool in a secret beach in Quintana Roo, Mexico. And tide pools are amazing because they don't only protect the shore from hurricanes, but also are little nurseries for biodiversity. The third essential element of biomimicry is ethos. So in order to have biomimicry as the axis of your professional practice, you have to have a bio-inclusive ethic, a bio-inclusive vision of the world in which all species are in a horizontal hierarchy, so to speak. Nobody has more value. Nobody is up. Nobody. That's a bio-inclusive ethic. So life creates conditions conducive to life. It does not poison itself. So we have to be respectful. And in the design professional practice, we are not going to pollute. We are not only going to think in sustainability, but ultimately in regenerative design. That is why in the photograph we can see two lichen species, Santoria parietita and Rumosa rudecta, in a rock in Tapalpa, Jalisco. Because we know lichen, we know fungi were the first ones to prepare this crazy planet for all life to happen. Now, we've learned the three essential elements of biomimicry, and now we're going to talk about the methodology itself, which is something else that makes it different from many other biodisciplines. So, biomimicry thinking has 6 steps. The first one is to define your challenge. We are talking about design, to define your design challenge. The second one is to biologize the function, the birth, and the context in which your design is going to perform. The third one is to discover what biological strategies are already tackling that challenge, so you can abstract the design principles from the biology and emulate them in your design. At the end of this methodology, you will learn to evaluate the fit and functionality of your design. Now, what I like to emphasize about biomimicry is that it is all about the verb. We will not think what we want our design to be, but what we want our design to do. And to achieve that, you have to think in verbs. This is an example. In the photograph, we can see a biodegradable water bottle made from agar-agar, algae-based polymers, biodegradable. However, we should ask ourselves, do we need, at this point of our human race, a biodegradable water bottle? Or do we need more efficient and sustainable ways to contain liquids, or to distribute liquids, or even harvest liquids, specifically water from the environment? So when you think about verbs instead of objects, there's a change in the way you design. If we choose the verb harvest, how does nature harvest liquids, specifically water? We jump into the biology, we do some research, and we find that the Namib desert beetle is already performing such function. On the right side, we can observe here is a micrographic photograph of the bumps that are on the shell of this beetle. And these tiny bumps are hydrophilic, meaning they attract water. And the channels between such bumps are hydrophobic, which means that they repel water. So when temperature goes down on the desert, it gets cooler. And these tiny bumps condense water from the environment, creating little currents in the hydrophobic channels that take all that water into the mandible of the insect. That's how the insect drinks water. Now, to end the theme of biomimicry thinking, we have to begin a systematic change. We have to think about ecosystems and how can we design in a regenerative way. So if we change the way we think and design, we are going to transform the way we produce and consume. And to produce and consume are not my favorite words because they are so anthropocentric, but it's the harsh reality of our species so far. And you may ask, what does biomimicry have to do with color? Well, in one word, everything. In one word, everything. Before we jump into fungi, let's go through the case studies of biomimicry and color. On the left, we have a photograph of the Discosoma coral, also known as the mushroom anemone, because the shape resembles a mushroom cup. And on the right, we can see the red fluorescent protein, which is responsible for this bright pink red color. Now, how does a protein create fluorescent color? Sorry, too many R's. On the center of the protein, we can observe this chemical structure. This chemical structure is called a fluorochrome. Now, a fluorochrome is a chemical compound which is a type of chromophore. Chromophores are molecules capable of changing their configuration when they absorb light. So the magic in Fluorochromes, as the one that has the red fluorescent protein of the Discosoma coral, is that they can re-emit light upon electron excitation. And the wavelength of such lights is going to be longer than the wavelength that they are absorbing. As we can see here in this figure, this is the rainbow, the visible spectrum of light. And the Discosoma coral, the electrons in the fluorochrome need an excitation from 558 nanometers wavelength, and they need to increase that into 583 nanometers wavelengths in order for the electrons to become excited and re-emit a 700 approximately nanometers wavelength that corresponds to the pink-red hue of the visible spectrum of light. Now, create and uses electrons. It's crazy. Here we have the chemical structure, a close composed by carbon atoms in whites, hydrogen atoms in blue, and oxygen atoms in red. Now, when two carbon atoms bond together, they create a p-bond that we have in this yellow color. And a p-bond is a way in which the electrons are being excited. Now, this is called the electron cloud model, and it was established in 1923 by Schrödinger, the guy of the cats that is dead and alive at the same time. If we go back to high school, perhaps you remember this atomic model that was established by Bohr in 1921. However, Schrödinger proposed this theory in which every little dot that we see in here is a potential place for the electrons to be buzzing and creating and absorbing energy. So there's a company in New York, and they do biotechnology. They apply biomimicry because they found a way to design a process in which they extract the red fluorescent protein from a tiny sample of the coral. Then in the second step, where it says microbial fermentation, they insert the protein into E. coli bacteria and create a lot of pigments with less money, let's sort of speak, and without using corals, living corals. So they can embed that color into the threads of the fabric and therefore have already colored fabric that does not need to be dyed. These are the results of the research. They are still in development and research phase. However, they've achieved several awards and being finalists in other awards. And we can observe in this photograph that they also achieved to extract the green fluorescent protein. And that protein comes from, oh, apologies, I don't know what's going on here. There you go. It comes from Equaria victoria jellyfish. So in this photograph, we can observe also the fabric they are creating, which is 100% biodegradable. It comes from algae also, and it already has the color that reacts under UV light, the fluorescent protein. So we've seen the first case study, and the second case study is the Bluemorpho Butterfly. On the right, we can see the Bluemorpho Butterfly, two different species, two different varieties of the same species. And on the videos, we can observe the Bluemorpho Eleanor Montezuma, which is a native species of Veracruz, Mexico. And if you see, that bright blue color disappears when light hits at a certain angle, but it's vivid under other conditions. How does this butterfly achieve such color? Well, there it is. This is a close-up of the wing scales of the butterfly. If we go a little bit closer, we can observe that each wing scale is composed by bridges. And these tiny, tiny structures that resemble a Christmas tree or a pine tree have these spaces between the ridges and are composed of chitin, the same biopolymer we have in our fingernails. So chitin is the second more abundant butterfly is creating structural color by the configuration of physical structures that are transparent. The cross ribs and the ridges are absorbing the full spectrum of light, but they bounce back only the blue wavelength. So we observe that in this butterfly and other cases of iridescence in nature, the physical structure of a material determines its optical properties. To this micrography, we have an illustration on the right, and it should be the full visible spectrum of light is absorbed and scattered in between these structures and only bounces back the blue wavelengths. That's why we see it so bright, because it's light itself, the wavelength of the sun, bouncing back at our eyes. And that mimicked this. I'll show you the video and after I'll explain. That liquid is a solvent, and inside that solvent there are many, many tiny structures like this one that resemble the structure of the wing scales of the butterfly, but they have different configurations, they have different physical properties, and therefore they reflect different spectrums of visible light, different wavelengths. So on the right here, we have a close-up of the structures that are floating in the solvent. And the distance between each of these branches, let's say, corresponds to a specific wavelength. The visible spectrum of light goes from the 700 to the 400 nanometers. So if they change the distance between these ridges, they will change the wavelength that bounces back. So we've learned the three essential elements of biomimicry, the methodology, we've seen the case studies of butterflies and corals, and now we are going to learn about color models. The two main color models are RGB, which is widely used in screens, and we can observe it in the butterfly because it's light itself creating color. And the second color model is CMYK, that is widely used in arts and design, in screen printing and printers. And this color is created using molecules using pigments and chemicals. RGB model is often named additive color mixing, and CMYK color model is called subtractive color mixing. First, the RGB color model, which is the additive. It is called additive color mixing. It is black. There is no color, there is no light. So you need to add light in order to create a visual representation, in order to create color. That is why it is called additive. The name RGB means red, green, and blue, which corresponds to the same colors of the photoreceptors we have in our eyes. We sense blue light, green light, and red light. And with a combination of such, we achieve all the full spectrum of visible light. In our eyes, we have photoreceptors, two kinds. The first one are named cones, and they sense the colors, the hues, the blue, the red, the orange, lavender, etc. And the second photoreceptors are called the rods. These photoreceptors are activated when the light is low, and they help us see in a grayscale. If we add all the wavelengths at the same time to a screen, we will obtain a white color, because in the RGB model, the sum of all colors is white. Now, for this color model, we've said the primary colors are red, green, blue, and the secondary colors are magenta, yellow, and cyan that create the CMYK color model. But before we jump into the other color model, I would like to explain to you a little bit of the chromaticity space. Chemists and physicists, they gathered, and in 1913, they created the International Commission of Illumination, because there was a need to regulate all the things of color science. This image on the right is called the chromaticity space, and it is widely used in computational design and user interface. At the border, we have these blue numbers that correspond to the different wavelengths of visible light. We have the green, we have the red, and we have the blue. And it is shaped in this way because it represents the perceptual unification of human sight. At the center, we have the sum of all colors, that is white. And if we want to know the secondary color of the mixture of the primary colors, we just trace a straight line and place ourselves in the middle. So in here, the mixture of the red and the green color will give a yellow color. If we place ourselves, oh, there it is, the yellow color, the cyan, and the magenta. So, CMYK color
Uh-oh. Ximena, we were missing your audio. How's everybody else's audio? Can you hear anything? Or is it just me?
painting.
Oh, we're back. Sorry. We
Yes.
lost you for a second there. If you could go back just a little bit, maybe start at CMYK. Oh. No.
And
It might help, Ximena, if you, it's not ideal, but potentially disabling video.
okay.
It might help the connection.
Is it better?
Yes.
Yes.
Is it better?
Yes, the last thing I heard was, is it better? I don't know if you said anything after that, though.
I did not. Okay, so.
Oh, okay, I thought you.
Oh, I'll go again with this slide in case it got cut. So the RGB color model is represented in this illustration, and this is called the Chromaticity Space. It was established in 1930 by the International Commission of Illumination in Vienna, Austria. The blue numbers that are on the border correspond to the different wavelengths of light, and it is widely used in computational design and user interface. If we want to find the mixture of two primary colors, all we have to do is trace a straight line and place ourselves in the middle. Therefore, the blends of green and red will result in yellow, as we observe in here. The subtractive color model, CMYK, it's called subtractive because you have to remove wavelengths of light from the media in which you are designing. Let's think that you have a canvas in front of you or a sheet of paper, and they are white because they are reflecting all the visible spectrum of light. Therefore, you need to subtract some of those wavelengths using pigments and paints. CMYK means cyan, magenta, and yellow. Now, this color theory is related with the other color theory, the RYB, which is red, yellow, blue, and is widely used in design. This color theory originated in the ancient Greece when Aristotle, Democritus, and Plato considered the four basic colors coming from nature, the four elements in nature: the yellow ochre from the earth, the blue of the sky, the green of the water, and the red of the fire. However, in 1510, Da Vinci proposed to remove the green color because it could be achieved by blending blue, to remove the green color, yes, because it could be achieved by blending blue and yellow. In 1613, Franciscus Aguilonius was a physicist and architect, and he was the first one to propose the trichromatic color model that we now know as the red, yellow, blue color model used in arts and design. This one, where if you blend yellow with blue, you get the green, yellow with red, you get the orange, and blue with red, we get the purple. When we talk about color theory and color models, we have to mention the color wheel. That is something we designers often use when applying color palettes to our designs. So the first color wheel was obviously designed by Sir Isaac Newton in 1665, and he did not add colors, but only the number of the colors in the same order of the wavelengths of the rainbow. In 1776, Moses Harris established what is called the prismatic circle, in which we have at the center the blue, the red, and the yellow colors, and all the possible blends outside this prismatic circle. And in 1810, Goethe was the first to provide in his color theory the subjective attributes of colors. That it is why it is so mentioned. He was really attacked at the time by scientists because he was providing subjective values to color, but he set the basis for the emotional theory of color. This is a photograph of my samples of inks, and we can observe that I applied the red, yellow, blue color model to create purple, orange, brown, and green using natural pigments. Now, on the left, we can observe Paul Klee's annotation on color. Paul Klee is very important because he was a professor at the Bauhaus School of Design, and he used the RYB color model, the one we've been mentioning very often, for the mixtures of paintings and pigments. And this is the color model that we actually use in natural dyes and natural pigments. On the right, we can observe this crazy diagram, and it's the Munsell color system. It is important because it's the first color system to consider light and darkness as part of the colors, and therefore is the first one to really take a deep look at shades of the same hue of color. So, color is light, light is energy, but what is light? Well, we know Sir Isaac Newton was the first one to perform this experiment and discover the rainbow, the visible spectrum of light. However, there was a debate at the time, in 1672, between Newton and Hooke, because Newton said that light behaves as particles. He established the corpuscular theory, meaning corpuscles are particles, and that's what light is made of. And in contrast, Hooke said that light was made of waves because light diffracts. And that means that when light hits an obstacle with a hole, it passes through as a rapid vibration. So Hooke could not visualize light as particles, but as waves passing through. We often believe that Einstein won the Nobel Prize in 1921 because of the relativity theory. However, he was awarded with the Nobel Prize because he discovered the photoelectric effect, in which he proved that light behaves both as a wave and as a particle. He established the term quanta, in which the quanta means photon, and a photon is the tiniest amount of light possible. So the photoelectric effect is when the emission of electrons when electromagnetic radiation, light, hits a material. They travel as waves, but they bounce back in the form of photons. He set the basis for quantum physics, quantum chemistry, and spectroscopy. Spectroscopy is really important because it's the use of light to unveil the elements, the atoms that contain certain molecules and how they interact with light. So, light creates color because it's electromagnetic radiation that behaves both as a wave and as a particle. On the left, we can observe this figure in which this is the electronic field traveling on the y-axis, and this is the magnetic field traveling on the z-axis or the x-axis, depending on how you see it. On the right, we can see the visible spectrum of light and the wavelengths that it has. If we have longer wavelengths, we can observe the existence of radio waves. And if we have shorter wavelengths, we go all the way to X-rays and gamma rays that damage DNA and disrupt life. In this chart, we can observe the values of each hue, each color, and the wavelengths and the frequency and energy that each of these colors has. Now, the wavelengths of light are measured, from crest to crest. And a wavelength also has amplitude, which is the distance between the x-axis and the y-axis. Now, this is very important because if we talk about shades and hues, energy and the amplitude of a wave plays a huge role in it. Short wavelengths mean high frequency, high energy, and they tend to be bluish. Long wavelengths mean low frequency and reddish colors, low energy. Now, the greater the amplitude of a wavelength, the brighter the color because it has more energy to bounce the photon in the interaction with the electrons. The smaller the amplitude, the duller the colors because it's less energy. So the frequency of a wavelength will determine the hue or the color, which is the same. And the amplitude of a wavelength will determine the brightness, meaning more energy, a greater jump of electrons, meaning more photons. Here's an example. We have different shades of lavender, and the brighter colors have greater amplitude, and the dull color has a lower amplitude. It has lower energy. And again, you may ask, that's really cool, but I'm here for the fungi. We need to understand light if we want to understand the photobiology and the quantum chemistry of fungi. If we want the right answers, first we need to ask the right questions to the right people. So, color in fungi. How does fungi sense and interpret light? And how and why fungi create color? We are going to try to answer these questions. So, fungi creates color and absorbs light inside the fungal cell. It creates color through its metabolism, and it creates color in its fruiting bodies of some species. First, inside the cell, we know color is light and light is energy, but energy also carries information. So how does fungi sense its environment and adapts to it? With the use of photoreceptors. Humans have photoreceptors in the eye, but fungi have photoreceptors in the cell. This is a cell of Neurospora crassa, an Ascomycetes, a filamentous fungi widely used to study the photobiology of fungi. So in this cell, we can observe the cytoplasm, and these are the photoreceptors, the phytochrome, the cryptochromes, sorry, many R's. These are the two that Neospora crassa has. And what's very interesting about photobiology is that when these molecules that are proteins, when these proteins absorb light, absorb sunlight, they trigger cellular responses. Spore germination could occur, vegetative growth, asexual and sexual development is determined by light. The fungi will know, depending on the shades of light and the metronomy of light, whether it's better to have an asexual reproduction or asexual development. It also affects the circadian clock of fungi, the phototropism, meaning how it will move towards light, the stress response. It triggers secondary metabolism, important in the creation of other pigments, the pathogenicity, and the nutrient uptake. So photoreceptors in the fungal cell are really, really important. Let's focus on this function, that is the secondary metabolism of the fungi trigger as a cellular response of the interaction of the photoreceptors with light. Remember the RGB model? Well, guess what wavelengths these photoreceptors in fungi absorb? The red, the green, and the blue. Phytochromes are proteins, photoreceptors in fungi, that absorb the red wavelength of light. Opsins absorb the green wavelength. And the PAST or LOVE, which means light, oxygen, and voltage proteins, this type of photoreceptors called cryptochromes, absorb the blue wavelength of light. This is a photograph of Neurospora crassa, that has the phytochrome and the cryptochrome in its fungal cells. As said before, Neurospora crassa is an ascomycetes, and these studies have been widely made in ascomycetes fungi. It's really interesting to see that many different fungi also possess these same photoreceptors. Here's the visible spectrum of light, and this is where every photoreceptor has a correspondence with the visible spectrum of light, with the wavelength size that they absorb. The main species that has been studied are Trichoderma atroviride, Neurospora crassa, Aspergillus nidulans, Alomyces reticulatus, Leptosphaeria maculans, Cryptococcus neoformans, Coprinus cinereus, which is a basidomycetes, and it's very interesting because there are few studies of photobiology of fungi made in basidomycetes, and the Botrytis cinerea that rots all delicious strawberries. You may ask about mycelium. Perhaps you're thinking, well, if this is a basidomycetes, this is the fruiting body, the mycelium underground, how is it capable of sensing light? Well, many studies have revealed that red light, that the red wavelengths of the visible spectrum of light is able to penetrate soil deeper than blue light. Red light can penetrate up to 2.5 centimeters into the soil, so it can reach mycelium and trigger cellular responses when it hits the photoreceptors in the fungal cell. Now, metabolism. Photoreceptors send signals to protect from UV damage. So in the metabolism of fungi, which is a cellular response triggered by the interaction of these photoreceptors with light, fungi produce keratin. Some species of fungi produce keratin because carotenoids absorb the blue-green spectrum of light, and therefore the orange-red visible spectrum bounces back at our eyes. Keratins serve the function to protect against UV radiation and oxidative stress. This diagram is called polyketide biosynthetic pathway. Now, a polyketide is any compound found in fungi or plants that has a biological function and could work as an antibiotic, for example. These are the chemical reactions that happen inside the fungal cells to achieve the final pigments, which in the Neurospora crassa species is named Neurospora xanthin and belongs to the group of the keratins. So, fungi time, so they can respond and adapt and create pigments. But how can a chemical compound express optical properties? The answer is quantum chemistry of fungi. We will not go very deep in such a short period of time, but the HOMO-LUMO gap happens when the electrons get excited, when they absorb light. In this diagram here, we can see energy levels, and the HOMO means the highest occupied molecular orbital. This is the ground state, existing in the way they are. However, when light enters and excites the electrons in the HOMO state, they become excited and jump to the lowest unoccupied molecular orbital. This means excitation of the electrons. So the energy gap that we have from the ground state of the electrons to the LUMO state corresponds to a visible spectrum of light, because every wavelength, each wavelength has a specific amount of energy. This diagram is the HOMO-LUMO gap of an anthraquinone pigment. And anthraquinone pigments are also found in Cortinaria sanguineus mushrooms. This is a photograph of Jenny Dean, the author of A Heritage of Color, and these are wool yarns dyed with Cortinaria sanguineus. So the pigment that is extracted from the fruiting bodies of the mushroom is actually performing this quantum chemistry at the molecular and atomic level. Here is the ground state of the electrons, and once they absorb light, we can see that they become excited. After they are excited, everything that goes up has to go down. And when they go down, they bounce back photons. So color happens in two ways. The energy difference that corresponds to a wavelength is when it jumps. And when it goes back to ground state, those electrons have to release the energy in form of photons. Therefore, we also see color in the form of wavelengths from the photons. And this that we observe as a second, perhaps, or a millisecond, is happening all the time. It's like as light hits the molecule, it's bouncing forth and back. It's being excited and it goes back. It's being excited and it goes back. And that's the continuity of color that we observe. If light hits the system for a long time, it will eventually provoke the bonds to break, because it's a lot of energy to metabolize. So color is our electrons interacting with photons and releasing photons in the form of wavelengths. And the wavelengths will correspond to a specific hue in the visible spectrum of light. In this chart, we can observe that the energy of one photon corresponds to the frequency of a wavelength and the size of such wavelengths in the visible spectrum of light. Color in the appearance and fruiting bodies of fungi can work as pesticides, repelling insects, as spore dispersal, attracting insects and pollinators, also as UV protection, and it could even function as DNA repair. Some carotenoids not only protect from UV damage, but also help reveal the DNA of the fungi. Hence, the anti-cancer properties of some fungi. They have the ability to reconstruct the DNA. Here we can observe Physolithos tinctorium, which is Dyer's puffball, Ipomyces lactiflorum, also known as the lobster mushroom, and Dios polypore Photobiology. Now, at last, but not least, we have this amazing human, Julie Wheeler. She's a mycodyer. Her project is called Mushroom Color Atlas. You can visit the webpage, mushroomcoloratlas.com, and it is a huge index of mushroom color. She does field studies, forest mushrooms, and experiment with them to see what colors can be achieved. We have shades from red, orange, yellow, and even blue, which is the most difficult color to achieve in a natural way. These are all the photographs. She gives workshops, and the International Fungi Fiber Symposium is approaching. I will tell you a little more about it. So Julie Wheeler, along with Alisa Allen and more people of the team, Alisa Allen has a project named Pigments, and they are the ones behind the International Fungi Fiber Symposium, which is going to be this October in Port Townsend, Washington. And on these photographs, we can observe these amazing greens achieved by using Photobiology or Dios polypore, and these other shades achieved by using Dios polypore, but altering the color with metallic salts. Now, we've covered a lot of subjects, chemistry and stuff, but it is not all. We didn't even talk about lichens. We don't know yet why these crazy boletus changes color and it goes from yellow to blue. We don't know how the pigments in the Dios polypore work. And we don't know what scientists are doing regarding fungal pigments. So this lecture is part of a series, and the part 2 will be about biochemistry, the species that create color, and the methods that scientists do, but we could also replicate at home to extract color from different fungi. And that will be all. Thank you very much.
Wow, everyone, that was so great. Thank you so much. I would love to turn on people's audio if you want to make comments. And if there are any questions that you all have now that you've absorbed all of that color and knowledge, definitely drop it in the Q&A. Lots of great comments and a few questions like throughout. There was one question that came up about the, let's go back, Angela, there was the name of the company that was using the materials to create the, I think the phosphorants or the
Yes.
fluorescent.
It's Cypress Materials, Inc.
Cypress Materials, Inc. Okay. Okay. Oh yeah, I see. I spelled it differently. Okay. Does anyone else want to make a comment? Samuel, do you want to say something? I know you're in Oaxaca too, or you're in Mexico as well. And I've been wanting you both to meet. So I did a program with the Austin Organic Gardeners with Samuel back last year, and he comes from a family of dyers, and they do the traditional Oaxacan rugs. And he talked about the cloud people of Oaxaca. But yeah, so he's here.
Yeah, hi. Thank you, Ximena. Muchas gracias. That was wonderful, amazing lecture and very inspiring. And in our culture, we do use some lichens for dyes. Mushrooms, not so. I mean, I guess some logs. Like but I've actually, it's lost, at least in my family. We haven't used mushrooms since I was born. And yeah, with Zach is bringing some people. I think he's bringing Julie here in his. So we collected some mushrooms last year because they know which ones, but like we didn't know how to use them. So now he's gonna bring Julie, and we're gonna learn. He's gonna run some workshops in Oaxaca to pass that knowledge to the locals here. So it's gonna be amazing, and yeah, very excited.
That's amazing.
Yes.
About color, how close are we getting to a point where I'm not sure if my video will work.
Okay. Oh, no worries.
Yeah, because I was involved in the sustainability field in my studies, and I came across the Biomimicry Institute and these case studies. And we know that, in the fashion industry, how colors, we use all these nasty chemicals to make colors. And I just, wanted to find out how close are we, in that industrial setting to mimic colors that way. If you could give us, a short answer.
Yes. Well, the thing about sustainability is the scale. Sadly, it will be amazing to replace all those nasty chemicals by natural ingredients. But if we think about plants, indigo, cempasúchil, pericon, the thing is the use of land. So we could be doing the same that agriculture is doing, having one single species of plants that will degrade the ecosystem of the soil, and we will be in the same place. We are far because everything needs to be at an industrial level. So if you have a sustainable practice and you want to scale it up at the industrial level, it will lose the sustainability because you will need more resources, more energy, more water, ways to distribute it. It will be just the same. So there's a phrase that I really like, a quote. I cannot remember who said it, but if the system is not working, don't try to break the system. Create a new one that makes the last one obsolete. So I believe that the start point is to rethink everything that we've learned, to rethink first the needs we have. Do we need all those clothes? Do we need to look that way? Do we need to give value to brands, or do we need to give value to processes and the people behind those products and those fabrics? So I grew up in Oaxaca. I love Oaxaca. And I believe that we need to re-understand that the value of things comes from the process and the people. So fashion industry is far away from incorporating micropigments. There are companies, Bio is in France. They use bacteria to create color. Pangaea is doing experiments also with bacteria. However, the prices are really high because you need bioreactors, laboratories, biotechnicians to control the conditions and avoid bacteria being killed by other bacteria. So we're far away still. However, at the craft level, we can create color from fungi.
Yeah, absolutely. I love that answer because, like I've been saying, the true definition of slow fashion is what our grandmas have been doing for thousands of years. They spend 6 months, 9 months creating a beautiful garment that will last them a lifetime. And they will keep repairing and mending it to pass it to their daughters and their next generations.
Precisely.
But I've been following also the work of these other podcasts, and they talk a lot about using yeasts and bacteria to brew things at a bigger scale. And, maybe, we're 7 billion people on this planet. And I guess there's two options. You still go the main industrial level where you create everything at a central location and then distribute it. or where you do more like nature, you know, we have cells that produce color at a little scale, and then we just have a lot of these cells around the globe. So incredible. Thank you.
Thank you, Simon.
Yeah, and if everybody caught, Kathy Zarsky is also here tonight, and she started Biomimicry Texas. I turned you on too. Let's see, turned your audio, and she shared the Biomimicry Institute's recent report on fashion in the chat. So definitely something to check out. Let me see. I'm gonna add you to the panelist, Kathy, if that's okay. I know I'm putting people on the spot, but I'm just getting all excited here. Let's see. Oh, there you are.
I'm here.
Thank you for coming tonight.
Yeah, that was an amazing presentation and beautifully done. I love that biomimicry really connects so deeply with people. So Angel and I did a biomimicry mycology walk at West Cave not too long ago. And I guess what I really wanted to say is, for those of you that I know are really excited about everything that you just heard and probably are craving an opportunity to learn a little bit more, is that we're going to do another walk coming up at West Cave at the end of May. We haven't opened up registrations yet, but put a save a date out there for 5/29, May 29th, to come and learn a little bit more and learn some of these observational skills. Biomimicry Texas has been kind of in and out of dormancies because we've done special events predominantly with South by Southwest over the years, but because we have so many new practicing professionals out around the world now, people are much more aware of all of the ways in which nature's wisdom is being applied to so many different fields. And it's so cross-disciplinary because you need the artists and you need the deep science and you need the business acumen. It really is a very multidisciplinary methodology. And we just really want to connect with everybody again and make it more accessible to people in Texas. So Angel, thank you for hosting tonight, because this was amazing.
Yeah, and this particular, Kathy mentions like different disciplines. So we'll have Teresa Morales, who is, she studied poetry. So we will be doing a poetry, like incorporating poetry into our observations and writing sort of sonnets and poems to nature. So it can be applied in a lot of different ways.
And Erin Rivolo's Eyesights will have her book available for people. Eyesights is a practice that is kind of at the beginning of your journey into biomimicry, just developing the lens of seeing. So I'm really excited to share that with everybody.
Yeah. Let's see. Kind of going through the chat here, and I want to check over on YouTube to make sure I'm not missing anybody's questions. Let's see, lots of great comments. Thank yous. Someone from Istanbul joined us. Must be, I don't know what time zone it is there. Hello, Istanbul. Let's see. Some knitters joining us. So yeah, let's see. Miriam from Mexico, huge fan of your work. All right. Buenos Aires joining us. Let's see. Thank you for this interesting talk. I wanted to share with you a project. I'm going to go, Heidi, is it okay if I turn you on? It's like a weird thing to say. I'm going to turn you on. Let's see. Heidi. Hello. I'm going to turn your video on too. That's okay. Can you hear us?
Yes. Can you hear me?
Yeah. Hi, Heidi.
Hi, everyone. I don't know if you can see me. I think I'm not. But it's okay.
Let me see if I can. I think I
No,
have
it's fine.
to.
It's kind of dark in here. So I just, well, thank you. I was following in YouTube and then I came into the, can you hear me okay?
Yes. Yes, we can hear you.
That's better. No, I was just following in YouTube and then it came in for the like last part on the Zoom talk. So it's really interesting. And I would just wanted to share that we're working on biofabrication from fungal biomaterials, and we're working on something called chromatic expressions, in which we are looking into the mycelium coloring aspect. So that is the thing that it's getting the color into the material instead of adding it. And we made like this color palette in which we tested the mycelium from Pigments sanguineus, and then we also tried dyeing it with food coloring, uh, gastronomic coloring, I don't know, from cochinilla, which I don't know the name in English.
Cochineal.
Okay. Yeah, so I think it's really interesting because there is not so much information about it. Like you have to dig in really deep into finding the ways to use this kind of colors, and Pigments is amazing. It's super powerful orange. So I just wanted to thank you and share the work with you.
Thank you, Heidi. I'm a huge fan of your work. I'm one of your greatest fans. When I saw your name, I was like, oh my God. And actually, if you allow me, since I'm in Daniel's lab, he's growing wild strains of Pigments sanguineus from Yucatan for my experiments. So let me grab a bag of Pigments sanguineus and show you the mycelium.
Oh, this is so exciting. Okay, I think we can see your video now. I just asked you to share your video.
Oh, yeah.
There you are.
Sorry,
Okay, good.
I wasn't expecting to be on camera,
So sorry.
but I'm happy to see this wild.
Yes.
I'm back. So here, I have to return it very fast because it's really hot and the fruiting room is at a lower temperature. But here we can see
Oh, yes.
the mycelium. This is not the fruiting body, it's the mycelium. And it's so bright orange. This is sorghum, I guess. It is growing on paper, recycled paper that we use to dry our hands. Well, I don't, but many people in restaurants do. Well,
Oh no, you cut out for a second. All of our videos running.
work in the fungal cell, we can trigger a greater response in color and growth by changing the light that we give to the mycelium. I'll take it back. I'll take it back because it honestly is really hot here in Merida. But I'll be back in a second. Ready.
I'm gonna go ahead and show you guys one of
Oh
the
my
ones we
God.
have here.
That is so beautiful.
This was from a bag from the ones that you had. Now we're working on some kind of products to see how we can get this in a more, I don't know if control way, but in a more kind of design where the color is going. So yeah, it's great to meet and connect. So we're now following you. The color is amazing. and it's just from the mycelium. So, and what we're trying to do now is trying to find out which other species are producing different type of material, the mycelium that can grow in a solid substrate in which we can use to form it. Okay, I don't want to take too much of the time. Thank you.
Great, amazing.
Yes, thank you. Julie. Julie.
Hello. Thank you so much. Ximena, your presentation was mind-blowing. I learned so much. It was just thrilling. So I'm just excited to be part of this.
Yes, thank you for coming tonight.
Thank you.
Oh, yeah.
I'm speechless.
Oh, well, I can't wait. I'm learning so much. I can't wait to find ways to collaborate with everyone and kind of advance the Mushroom Color Atlas to include this work and these studies that are being done. So to, raise awareness of it and reach more people so that they can learn about this amazing work that's being done with fungi and mycelium. So
Yes.
thank you. Thank you. Thank you.
Thank you, Yuli. I'm a huge fan of your work. I love what you do, your passion, the energy that you have. It's so beautiful that
Thank you.
I cannot believe you're seeing me right now.
And likewise. And I can't wait to meet you in person at the International Fungi and Fiber Symposium. And I want to find a way for you to present this incredible work to the attendees there. So we're going to have to chat.
Yes.
Yes. Thank you.
Yeah. Thank you.
Okay, Kathleen, you had your hand raised. I promoted you to be able to talk, and if you accept me being able to promote you to a panelist, I can turn on your video.
No, I don't want to.
Okay, no problem.
This is the first time I've ever talked on one of these too, so it's this is a real leap. What my question is, I live in Gibsons on the Sunshine Coast, just outside of Vancouver, and mushroom dyeing is really popular here. We're really close to Washington, D.C. I mean, not D.C., but U.S., Washington State. And when I'm out mushroom picking, you bump into people and really interesting off-grid oddballs. And that's one of the best things about it. It attracts a certain type of being. And there's one person that I bumped into, and he builds these mountain bike trails that are really popular. And I got talking to him about the phosphorescence that people are discovering, and it's transferring to their fibers. And of course, this one young woman who goes to raves and stuff thought, whoa, my hair is protein. And she did her hair for a rave. I just thought that was so awesome. And I talked to him about it. I was up looking for a red belted conch as a Christmas gift for a friend. So it was just before Christmas and a break in the rain. And there he was. And I talked to him about that. And he said, oh yeah, when I'm riding through the woods at night, I can see them glowing like jewels off in the forest. And of course, you're in the forest at night, like that's no way, and he's riding on his mountain bike. So anyway, the last time I talked to him, I got a little more information, and he has a light that just directs right on the trail from his bike and his head. So he's not splashing the light out into the forest. And he's built the trail, so he's very safe. But he said, yeah, you see them glowing. I think all kinds of mushrooms have phosphorescence that we don't even know about. Mm-hmm. And my Irish grandpa used to call that fairy wood. The wood that left over the punky stuff that's full of mycelium. He'd say, no, this is fairy wood.
Wow.
Yeah. Anyway, that's a story from the Pacific Northwest. to you Southerners.
Yes. Thank you for sharing that.
That's really beautiful.
So Betty, you have your hand raised. You should be able to ask your question now. Are you able to ask your question?
Maybe make sure, Betty, that you're unmuted.
Yeah, I see you're on mute. Does anyone else have a question? Like to talk? Well, I'm not seeing that anybody else with their hand raised. Oh,
Betty, if you need any IT support, if you scroll down to the left, you should be able to hit unmute. I'm not sure if that's the issue or not, but.
anybody out on YouTube have a question? I see a lot of comments. Thank you from Bermuda.
Wow.
I love this. Vancouver, Canada. This is beautiful, everybody. We're myceliating all over the globe, making color through RGB screens.
Yes.
We're not doing it. Those big tech giants are.
I do have a question.
Yes.
If that's okay. It's kind of a big one, and it's really just more some thoughts that I have. So for me, color theory and design, as with I'm sure every other artist and designer on here, is very esoteric. And so I wanted to pose some thoughts and questions about language and cosmology. I'm also really excited that Samuel's on this call because I know that you reference and speak much about your own original language and the cosmology of your family and community and how your language reflects that. I really resonate with that and think it's really beautiful. And Ximena, at the beginning of your presentation, you referenced a misguided and, in my words, a mythical belief system that we are separated from nature. And I wanted to highlight that the word biomimicry itself means to imitate life. So even within that word and term, and as language is cosmology, within that term, there's still a perceived separation embodied and embedded in that word. And so how can we in fact imitate life if we recognize that we are in fact life? I really resonate with the words reflect or realign. Also recognize that we're speaking in English, and at this point in time, it's become a very limited language. So yeah, it's the first part. And then also in your exercise at the beginning, you noted how few people visualize other humans, other people in their natural surroundings. I think that there's obviously a lot to unpack there, but is especially prevalent in Eurocentric thinking. And in what ways can we lift up cultures and communities who presently and historically, and will continue to do so in the future, that are aligned with what we perceive and define as biomimicry design? Because all the examples that I'm familiar with and have learned from within the biomimicry sphere looks to non-human teachers. And I think that there's a lot of erasure that happens there. So those are all my thoughts. And I think that they're exciting things to think about. And wanted to see if anyone had anything to say to that or any similar thoughts.
Yeah, it's a lot to think about. And I think, Samuel talking about this sort of delineation and talking about scale, right? And, essentially
And grandmothers referencing
grandmothers, yes, like doing what now is considered craft in like the Western world, right? Like these sort of things don't fit into this sort of extractive model of corporate capitalism and scale. And so, you know, Ximena, you were saying, you know, we have to build something new and show people something new and slowed down, you know.
Yes. It's really interesting, Emma, what you say, and you're absolutely right. Because if we say that we have to imitate life, we are not seeing ourselves as life. So we might have to even rethink the whole concept of biomimicry, because biomimicry is still having an anthropocentric view in which you want to learn from nature so you can replicate it. So this, well, Eurocentrism way of seeing production and crafts, as you say, Angel, has permeated even into sustainable practices. We have to rethink everything, and we have to decolonize our languages, as Emma says, because yes, crafts are named crafts because they do not fit, as you said, Angel, in the productive manufacturing system. Mm-hmm. But what if crafts, well, actually crafts are more valuable than any manufactured product. So this new system that we might create has to decolonize even the way we communicate and the way we create, to dignify the ancestral knowledge that has mistaken and not good by the colonizers. So it is really important to decolonize everything, because we've proven to have, indigenous communities in Latin America have proved to have more sustainable practices, and it goes back to the scale as well.
Mm-hmm. Yeah, so, and with not just scale, but it's culture versus profit.
Yes.
And that's everything. Like,
yeah. Precisely, yes. And see, and recover and dignify what really has value, because in modern society, a digital electronic object has more value than a plant. Mm-hmm. And it has to do with the lifetime, with the life of products. We value more that what has a longer life cycle, but we need to understand that nature and natural things will not last forever. And that's the beauty of it. And that's the value that it has, that it will only exist for a certain amount of time. So timeless things are not really valuable. What exists in a short time, in a short period of time, has more value because it will not be there forever.
Mm-hmm. Sam, were you wanting to say something?
Yeah. I mean, that's a great question and great topic. And I think up to this point, what's at stake is we're trying to redesign our production and consumption system. Right now, it's outgrown. It's so big, you know, but we still have those pockets of what I've been calling like the indigenous production systems, like here in the Central Valley of Oaxaca, and I'm sure in many other places and bioregions in the world. Here, like different communities specialize in a craft. And you know, we have northern communities in the Sierras, the Central Valley, and the Southern Sierra. And as far as the coastal regions of the Pacific, and then we trade in this, like, you know, shorter network of communities that make us self-sufficient. So you have the pottery makers, the sandal makers, the weavers, and you know, all the other fruit and vegetable producers in a network that's much smaller, and that I think I'm still trying to think about this. You know, how can we you know, like break apart, you know, this huge system where it costs 1 cent to bring a product from China on a container and then to be sold at a mall in New York. It's we're having to redesign that. And like Ximena was saying, I think it's about the verb. What function are we and what need are we trying to meet with this product? Is this a need, a desire, or an expectation of a product? Do we really need it? And then how could we meet this need in the most sustainable way? And I was impressed when I was reading about the sea people in Southeast Asia, because they spend so much time at sea that they get land sick, and they have evolved so that their children have a thicker retina than humans, than your average human. So they themselves are the technology. They push their bodies to the limit that they're the sea people. So they've adapted to their environment, and they fish and swim, and they're negative buoyant, and they have all these amazing skills to live in harmony with their environment and to live in connection with their food source, and they meet their clothing need with their own body technology. So I was just thinking about that example when we were talking about how we are perceived as being removed from our environment, from nature. And I think we'll definitely have to reroute our industrial system so that it's rooted in more ancestral knowledge and more connected with nature. This is what, in poetic terms, we talk about, like mending that fabric of life that connects us humans to nature.
Yeah, I think a lot of what you just said, I thought about relationships and families or communities, but also with our land and mending those relationships as well.
Good conversation. I'm glad we're having this tonight. And thank you, Emma, for bringing these important things up. Because semantics really do drive actions. And, this goes back many, 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 many thousands of years, and prehistory too. Like, we only know so much of how these indigenous lifeways have been constantly reconstituted, rebranded, repositioned semantically for the sake of profits over people or over nature. I mean, I'm separating it again, like the planet, Earth first, all living things, including the microbes.
Oh, yes.
Yes. Does anyone have anything else to add tonight?
There's a lot of really exciting people on this call, and I know I don't know most of you personally, but I'm familiar with a lot of y'all's work, and some of you are new to me, and I just really appreciate that and think there's a lot of energy and synergy here, and really cool to see everyone who attended.
Yes. Yeah. Well, thank you everyone for being part of this tonight, and thank you, Ximena. Thank you, James, for your translation. And please join us on May 1st. I know I put it in the chat and I didn't announce it at the beginning, which I was supposed to, but we're doing a Shibori dye class. Ximena, do you want to maybe share?
Yes.
Okay.
There it is.
Yes. So please join us. It will be online, and there will be a recording for everyone. We'll have a supply list that goes out. And if you don't have fungi available where you are, we'll have some substitutes things you can use instead that are readily available. And so yeah, so please do join us and check our website for upcoming events. And as Kathy had shared, we were going to do another walk. It'll be in the spring season, our Entangled Nature series. And we will be writing poetry, drawing, and doing exercises to entangle ourselves into the natural world at West Cave, which is a beautiful ecosystem in just west of Austin. So yeah, so thank you again, everyone, for joining. And if we don't have any other questions, we will sign off. And everybody have a good night. And thank you again, Ximena.
Thank you, Angel. Thank you, Emma. Thank you, Sam. Thank you, Jamie. Thank you, James. Thank you, everybody.
Thank you. It was so amazing and exciting. We learned so much.
My pleasure.
Can't wait for part 2.
Yay!
All right.
Okay, good
Bye.
night.